Good morning everyone. Today we are going to present our seminar on jump search algorithm. Jump search is an efficient searching technique used for sorted arrays. It works by skipping elements in fixed size blocks instead of checking every element one by one. In this presentation, we will discuss its working principle, algorithm, implementation, complexity analysis, advantages, disadvantages, and applications. Before learning jump search, let's understand why efficient searching is important. In large datasets, searching an element one by one can take a lot of time. For example, if we have 1 million records, linear search may need up to 1 million comparisons. Different searching algorithms provide different level of efficiency. Linear search has a time complexity of big O of n. Binary search is very efficient with big O of log n. Jump search lies in between with big O of root n, providing a balance between simplicity and performance. Jump search is a searching algorithm designed for sorted arrays. Instead of checking every element, it jumps ahead by fixed intervals. The optimal jump size is the square root of the number of elements represented as root n. The algorithm works in two phases. First is the jump phase where blocks are skipped. Second is the linear search phase where the target is searched within the identified block. This reduces the number of comparisons compared to linear search. For jump search to work efficiently, some conditions must be satisfied. The most important requirement is that the array must be sorted. If the data is not sorted, the algorithm cannot decide where to jump. Another requirement is random access. This means elements should be directly accessible using indices. Therefore, arrays are suitable while linked lists are not. Jump search also performs best on relatively static datasets where the data does not change frequently. Let's see how jump search works with an example. We want to find the element 42 in a sorted array of 9 elements. The jump size is root 9, which equals 3. First we jump to the index 3 and find the value 22. Since 22 is less than 42, we continue jumping. Next, we jump to the index 6 and find the value 55. Since 55 is greater than 42, we know that the target must lie between index 3 and index 6. We then perform a linear search within this block. After checking 30 and then 42, we find the target at index 5. This example clearly shows how jump search narrows the search space efficiently. This slide shows the pseudocode of jump search. First we calculate the jump size as root n. Then we repeatedly jump through the array until we find a block that may contain the target. Once the correct block is identified, a linear search is performed within that block. If the element is found, its index is returned. Otherwise, the algorithm returns -1. Now I hand over the presentation to Anjana, who will explain the implementation and analysis.
This program implements the jump search algorithm for searching an element in a sorted array. First, we include the header files. The math.h provides the sqrt function needed to calculate the jump size. The jump search function takes three parameters: the array, the target element x, and size of the array m. Inside the function, the jump size is calculated as the square root of n. The value determines how many elements the algorithm skips during each jump. The variable prev keeps track of the starting index of the current block. The first while loop represents the jump phase. The algorithm checks the last element of each block using fbin to ensure the index remains within the array bounds. If the target element is larger than the current block's last element, the algorithm jumps to the next block. If the starting position exceeds the array size, the function returns -1, indicating that the element is not present. Once the correct block is identified, the second while loop performs a linear search within that block. The variable prev is incremented one position at a time until the target element is found or the end of the block is reached. After the linear scan, if the current element matches the target value, the function returns its index, otherwise it returns -1. In the main function, a sorted array is created and the target value 42 is searched using the jump search function. The returned result is stored in the variable result. If the result is not -1, the program displays the index where the element was found. Otherwise, it displays a message indicating that the element was not found. This implementation demonstrates how jump search combines block jumping and linear searching to achieve a time complexity of order of root n, making it faster than linear search for sorted arrays. Now let's analyze the performance of jump search. The jump size is chosen as root n. In the worst case, the algorithm performs about root n jumps and root n linear comparisons. Therefore, the overall time complexity becomes order of root n. The best case complexity is order of 1 when the element is found immediately. The worst case complexity is order of root n. The space complexity is order of 1 because no extra memory is required. Jump search offers several advantages. It is faster than linear search for sorted arrays. It is easy to understand and implement. It reduces the number of comparisons and requires only constant memory. However, it also has some limitations. The data must be sorted. It is slower than binary search on very large data sets. Its efficiency decreases as the dataset becomes extremely large. It is also not suitable for linked list because random access is required. This table compares linear search, jump search, and binary search. Linear search is the simplest but least efficient. Binary search is the fastest but slightly more complex. Jump search provides a balance between the two. Some real-world applications include sorted databases, file systems, game development, and embedded systems. It is especially useful when the data is sorted and a simple implementation is preferred. To conclude, jump search is an efficient searching algorithm for sorted arrays. It works by combining block jumping and linear searching. Its time complexity is order of root n, making it faster than linear search while remaining simple to implement. The algorithm requires a sorted array and random access to elements. Thank you.